Great. So, hello, my name is Rebecka and I'm from the University of Geneva in the group of Hugo Zbinden. So today I'll present our work on high-speed integrated quantum key distribution. So this work has been done in collaboration with the Politecnico in Milano, as well as InGaAs in Geneva, Sequoia in Berlin, and the Center of Nanotechnology and Photonics in Milano. So an overview of the presentation. So first I will introduce the protocol we use. Then I'll explain how we go from a fiber-based to an integrated QKD setup. I'll then explain and give some details about our integrated transmitter, the same for our integrated receiver, and then I'll share with you some of our most recent results. So firstly, starting with our protocol. So we use the 3-state time-bin BBD4 protocol with one decoy state. So as the title suggests, we use time-bin to encode our quantum states. So here we have our time-bin. This is an early pulse. This is a late pulse. So we can encode either in the Z basis or in the X basis. If we encode in the Z basis, correctly detected states here will constitute the raw key. So for example, we can encode in state 0, which is linked to bit 0, which consists of a pulse in the early time bin and nothing in the late time bin. And inversely for the state 1, linked to bit 1. We can also encode in the X basis, also the monitoring basis. So states encoded here are used to monitor any eavesdropping that has been going on throughout the secret key exchange. So here we encode in the plus state, which is a superposition of the 0 and the 1 state. So we use weak coherent pulses, and to be robust against photon number splitting attacks, we use the one decoy state protocol. Hence, we encode in 2 different mean photon numbers, mu1 and mu2. So how is this implemented? So I here show you a schematic of our fiber-based setup. So we gain switch our laser to produce phase randomized pulses at the frequency of 2.5 gigahertz and at the wavelength of 1550 nanometers. So the pulses pass through a narrow bandwidth filter and then into an imbalanced Michelson interferometer. So here we have a delay line of 200 picoseconds. So pairs of phase correlated pulses will be produced, and these are our qubits, so separated with 200 picoseconds. These pulses then enter our intensity modulator, where we encode our states. Then we pass through dispersion compensated fiber and a variable attenuator to attenuate down to single photon level. We then exit our transmitter and go through single mode fiber into our transmitter receiver, Bob. So on the receiver side, we first have a beam splitter where light either goes to the Z basis. So here, any detections will be a simple time of arrival measurement, and the correct detections here will constitute the raw key. Light that goes into the X basis detector will pass through an imbalanced Michelson interferometer, exactly the same as on Alice's side with the same delay line. And so here, the interference of the central interference peak here will be, so we will have interference of the central interference peak, and the phase is set actually between Alice and Bob such that we will have destructive interference, and in the X basis detector we control. So Alice and Bob are controlled with FPGAs, and they are linked via a service channel. So now, with in mind wanting to further develop QKD and eventually industrialize QKD, a natural step is to go towards integrated platforms. So there are several advantages of this. Not only can we reduce the size, which is practical from a user point of view, size, and also, but we can also lower the costs, mass produce, etc. So for the rest of the talk, I'll now introduce our high-speed integrated QKD system. And so here we see an image of the transmitter chip that we have. So I'll go into detail about this in just a minute. So first, just to compare, so here on the left, we see our fiber-based transmitter and some components that are now on our integrated transmitter. So this is actually to scale, just for comparison reasons. So this little blue point is now the integrated transmitter. So for the details about the transmitter Alice, so Alice is based upon silicon photonics, and it's been developed in collaboration with Sequoia in Berlin. So, okay, as you can see here, it's very small. It has a footprint of 1.1 millimeters times 4.5 millimeters. So the optical part of the chip is this. So here, fibers coupled into the chip via a grating coupler. What we see next to it is the electronic part of the chip. So here we have our intensity modulator driver. So for example, digital to analog converters that will control our phase shifters of the intensity modulator of our chip. So just some comments about the choice of platform of silicon. So we have a small footprint. We can integrate both the electronics and the photonics, and it also allows for fast modulation. Maybe a disadvantage of using silicon is that we cannot integrate a laser onto this chip. So our laser is off chip. So for the structure of the optical part of our chip, so we enter from our laser in one of two entrances. So either through a ring filter or directly into an imbalanced Mach-Zehnder interferometer. So similar to what I showed you before, we need an imbalanced interferometer with a delay line of 200 picoseconds. So here we have heaters in each arm with which we can change the phase, and even an attenuator in the short arm to simulate the losses of the longer arm. Pulses then pass through an intensity modulator where our states will be encoded. So here through 3 different sized phase shifters. So in order to produce the full combination of the 6 states that we want, we also have heaters in both of the arms here. Finally, you pass through a variable attenuator where we can attenuate down to single photon level. So this we can do either by adjusting the heaters of our of a Mach-Zehnder interferometer. We can actually monitor any light on this photodiode, or there's another similar attenuator as in the interferometer, which we can use to also attenuate. Then we have managed to encode our quantum states, and we can go out of the transmitter chip into our receiver. So that brings me to the receiver side. So the receiver bulb is based on silica. It's fabricated at the Center of Nanotechnology and Photonics in Milano in the group of Roberto Osellame, using a femtosecond laser micromachining technique. So here's an image of the chip. Again, some comments of the choice of platform. So some advantages of using this is that we have low losses in this chip. It's very important on the receiver side. So we have around 3 dB losses, and this includes in both bases, and this includes the coupling losses as well as propagation losses. Also, this chip is polarization insensitive, which means that so the beam splitter for the X or Z bases is insensitive to the polarization, as well as the visibility of the imbalanced interferometer bulbs. So this is something which is quite tricky to have in integrated photonics because of the intrinsic birefringence. And this birefringence is something that could be controlled at certain temperatures in the group of Roberto Osellame. Okay, some disadvantages is that, again, we cannot integrate here a detector. And one could say that has a rather large footprint of around 8 times, because it's around 8 times 6 centimeters squared. So it's slightly bigger than the previous chip. So again, just here an overview of the optical part of our chip. So we enter into a 90-10 beam splitter. So 90% of the light goes out towards the Z base's detector. The detectors are off chip. or 10% of light goes into this Mach-Zehnder interferometer with a 200 picosecond delay line, again, the same as on Alice's side, and out towards a detector. So for the full experimental setup, we have here an external laser coupled into the chip of Alice. Here we can encode our states and attenuate them down to single photon level. We can place single mode fiber in between, and we go to the receiver. And here we have single photon detectors that are off chip. So Alice and Bob are both controlled via FPGAs and are linked via service channel. So this allows us to produce a secret key exchange real time, and the error correction algorithm that we use is Cascade. So for now, the results. Firstly, we used superconducting nanowire single photon detectors, SNSPDs. This we use more for characterizing our setup to get a hint of the best performance we can have. This is because these detectors have very low timing jitter and after pulse probability. However, they have to be cooled down at cryogenic temperatures. And so this can be seen to be it's not really in the same spirit of integrated photonics to be very practical, as it's not very practical to pull this down. So for the rest of the results, we used indium gallium arsenide indium phosphide single photon avalanche photodiodes that were cooled down with a Stirling cooler at around -85 degrees. So these detectors could be seen as being a bit more mature for real world implementation in that sense. So starting with the results using the SNSPDs. So there are many things to say here. First of all, the distance. So first in attenuation, this means this is an emulated distance. So I attenuated using the attenuators of the integrated transmitter. So at 30 dB, we have a quite raw high key rate, low QBERs and phase error rate, and we achieve a high estimated secret key rate, estimated because we did not use real-time error correction here, as the attenuation was too low. However, for results of distances from 36 to 40, we could use this error correction. So we get raw key rates, which are, well, following this results, they're still quite high, low QBERs and error and phase error rate. One comment, the phase error rate is slightly higher at 40 dB. This is normal because we have quite low amount of detections at 40 dB in the X bases, and so a bit harder to stabilize. Then we place 200 kilometers of standard single mode fiber, and we achieve here a slightly lower raw key rate than at 40 dB. This is okay due to maybe, I think we're slightly underestimating the distance, and also we have some additional losses maybe from splicing or connectors. However, the QBER and the error rate and the phase error rate are still quite good, as well as the secret key rate. Now, what's interesting to compare with are the results obtained in the group using the fiber-based setup. So at around 3 dB more emulated distance, we achieved slightly lower than half of the raw key rate, with similar QBERs and phase error rate, and around half of the secret key rate. So we can conclude here that the results we obtain with our integrated system are at least as good, or actually slightly better than for the fiber-based setup. So this we're quite happy with. Now going to the results using the InGaAs detectors. So again, here we use an emulated fiber distance from between 30 to 40 dB. So first comment is that the raw key rate is much lower. This is also quite normal. We have here an efficiency of at least a fourth of the one of the SNSPDs. So the QBERs is higher than before. This is also due to increased jitter of these detectors as well as after pulsing probability. And so we have a following secret key rate, which is totally acceptable and quite nice. Again, we can compare with results obtained in the group using the same detectors. We see directly here that it's maybe the raw key rate is a bit higher for similar QBER and phi-Z, and so a slightly higher secret key rates, although we're still in the same order of magnitude for sure. One comment to make here would be that, so first of all, the splitting ratio at Bob's is not quite 90-10, but more 94-6. So we have a bit less light than expected in the X bases and a bit more light as expected in the Z bases. We're quite fast we're saturating in the Z detector. And at the same time, we're close to the dark count and dark counts in the X detector. So the different parameters we can change of these detectors, such as the dead time, the bias voltage, and even the temperature, we're all set to be the same for the three distances here. But we could expect at least as good results if for each distance we optimize these parameters. So yeah, in conclusion, we showed a high-speed integrated QKD at long distances with competitive secret key rates and low QBERs. We could do some final tweaks to optimize maybe the last results, but overall, we're quite happy with these results. Thank you for attention, and thank you to the QKD team in Geneva.